What's up, everybody? Homework tonight, you are doing a bunch of limit definition of derivative problems. Sammy Soul asked for a video, so here you have it. Shout out, Sammy. Thank you for that idea. I'm sure it will help people if they watch it. So what we're saying is we want to find f prime of x, which is our slope function, m of x, our slope function for the original function f of x, which is x cubed. So we want to find the derivative of x cubed, which will be a function that tells us our instantaneous slope at whatever x value we want. And to do that, we need to take the limit as h approaches 0 of f of x plus h minus f of x over h. And what this is saying, essentially, is it's just another fancy version of slope. So h would be the difference in x of 2 points, and at the top we have the y differences of those 2 points. So h is like our delta x. Okay. So how do we do these problems? Well, if we substitute in with our function, we're looking at the limit as h approaches 0 of f of x plus h. Well, f of x is x cubed, so f of x plus h is x plus h cubed minus f of x all over h. So we need to expand x plus h cubed, and to do so we were using what we did in class with Pascal's triangle and the binomial theorem. So let's recall that real quick. If we want to generate Pascal's triangle, we start with 1, and then we do 2 1s there, and now we start adding things. So 1 plus 1 is 2. We always have 1s on the end. 1 plus 2 is 3. 2 plus 1 is 3. We keep going. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4, and then we have a 1 on the end, right? And you could keep doing this forever, and we get patterns in the numbers, and we like it because it helps us to expand things. So if I want to do x plus h cubed, well, that's going to give me an x cubed plus an x squared h plus an, what do I want to write? Plus an x h squared plus an h cubed. So notice our x's are decreasing in their multiplicity as we move from the left to the right, and our h's are increasing in their multiplicity as we move from the left to the right. But in each instance, our powers always add to 3. So x cubed, well, there's our 3 power. That's why we don't have any h's there. It's like h to the 0. Our next one, x squared times h. Well, h has a power of 1, x has a power of 2, so we get our power of 3. X h squared, x has a power of 1, h has a power of 2, so we get our 3 powers. And the last one, h cubed, we get our 3 powers. And now we need to use Pascal's triangle to help us with this. And we look at this row right there. It's telling us those coefficients are 1, 3, 3, and 1. And if you want to do x plus h to the 4th, you would use the row below that. X plus h to the 5th, you would use the row 2 below that. So we know these two things are equivalent, which means over here in our limit problem, we're looking at the limit as h approaches 0 of x cubed plus 3x squared h plus 3x h squared plus 1h cubed. That's x plus h cubed expanded. And then we have to subtract f of x, which is x cubed. All of that is still divided by h. And what I want you to notice is that our first term, x cubed, cancels with that last term, negative x cubed. So those are gone. Everything in the top has a power of h in it, so we can factor that out. So let's rewrite this as the limit as h approaches 0 of, pull an h out front. What's left behind? Well, 3x squared plus 3x h plus h squared, pulling out 1 power of h in each of those. This is all over h. What do you notice? We have a hole, so we take it out. So we're left with the limit as h approaches 0 of 3x squared plus 3x h plus h squared. And now we can directly substitute in 0 for h, and we're left with 3x squared plus 3x times 0 plus 0 squared. And so those last two terms go away, and we're left with 3x x squared. That is the value of this limit. It is a function. This is our f prime of x, which is just the slope function of f of x. So you're doing this for all of those binomials, x plus h, all those functions, f of x to the power of something, from 1 up to 7. So hopefully you can take it from here.